Of course, one small detail is if you were to look at the field inside the dipole, then it would be from positive charge to the negative charge. It would be in the opposite direction of the dipole moment. But remember, this is the field far away from the dipole, right? So when I'm looking at that field, I'm not looking at the field inside the dipole. I'm looking at the field far away from the dipole. So I'm always looking at the field outside the dipole. So remember, this is the expression for far away outside the dipole. The second major difference we are seeing between the radial and the dipole field is that the radial field only depends upon the total charge. Whatever is the total charge. If this was not a dipole, then it will only depend on the charge. But look at what the dipole field depends on. The dipole field depends on the product of the charge and the distance between them. If I had another dipole, or if I took the same dipole and let's say I doubled the distance, but I made the charge value half, the product would stay the same. And so when I go far away, it feels like it's the same dipole. So the identity or the strength of the dipole is not in their charge or in the distance, but it's the product. The product decides the strength of the dipole. The product decides how strong the field is going to be. And that's the reason this product for a dipole is given a name. It's called the dipole moment, which is represented by P. And so finally, we can now write the expression for the electric field on the axis is 2 times K, which is the Coulomb's constant, times P divided by R cubed. And what is the direction of this electric field? You can see over here, everywhere to the right, the electric field will be towards the left. What if I go towards the left of this dipole? The electric field would still be towards the left because positive charge will be dominating, and so it will be pushing. And so again, if we go back to that, you can see everywhere on the axis, the electric field is to the left. So let's come back over here. And it's for that reason we said, let's say the dipole moment is also to the left. The direction of the dipole moment is also taken to be towards the left. So the dipole moment is from negative charge to the positive charge. And so we can say everywhere on the axis, the electric field is in the same direction as the dipole moment. And so vectorially, I could say they have the same direction. Of course, one small detail is if you were to look at the field inside the dipole, then it would be from positive charge to the negative charge. It would be in the opposite direction of the dipole moment. But remember, this is the field far away from the dipole, right? So when I'm looking at that field, I'm not looking at the field inside the dipole. I'm looking at the field far away from the dipole. So I'm always looking at the field outside the dipole. So remember, this is the expression for far away outside the dipole.
So the electric field of a point charge was something that we were given from Coulomb's law. That is something we just discerned from the force between two charged particles. We can discern the electric field from that. And the philosophy that we're going to take in this course is that the way to calculate other more complicated electric fields is to simply treat them as the superposition of a bunch of point charges. So we had talked about that superposition idea, that the total electric field is the vector sum of all the electric fields contributing to that point in space. And so using that idea, then, we talked about what would be the electric field of a ball of charge, of a charged sphere. So a uniformly charged sphere, we said, would then look like, if I was far enough away from the charged sphere, that electric field looks just like a point particle. And in fact, it remains looking just like a point particle no matter how close you get to the surface of the sphere. Until you get inside it, then it looks completely different. But as long as you're outside of the charged sphere and the charge is uniformly distributed on the surface of that sphere, from the outside, it looks like there's a point charge centered at the center. We also used the same idea to calculate the electric field of a dipole. We defined a dipole as two charges oppositely charged, positive and negative. And then to find the electric field around that, we just did the vector sum, the superposition of the electric field from the positive point charge plus the electric field from the negative point charge. All right? And we found that it goes like this. The electric field comes pointing out of the positive charge, loops back around and points into the negative charge. It turns out that it looks just like the magnetic field from a bar magnet, and there are good reasons for that. So here is the summary of what we calculated last time for the electric field coming from a dipole. So here I've oriented the dipole moment along the y-axis. This is x-axis, y-axis, and z-axis. And I have a plus q and a minus q. That makes up a dipole moment. Right? The dipole moment is q times the distance between these guys. And then we saw that the electric field coming out of the y-axis here, it's oriented along the y-axis. So up here along the y-axis, far enough away from the dipole, we found this equation for the electric field. It goes like 1 over 4 pi epsilon naught, 2sq over r cubed times y hat. Your book favors a different type of notation for vectors. Your book favors the three-component notation. Here, y hat is a unit vector that points in the positive y direction, which in this diagram is up. And in the three-component notation, this would be 0, 1, 0, a unit vector that points in the y direction. So all along here, along that y-axis, this is the form of the electric field. And it falls off like 1 over r cubed. So as I get farther and farther away from the center of the dipole, put the center of the dipole at the origin, as I get farther and farther away, the electric field falls off like r cubed. Over here, it's a very similar looking electric field. The main difference is that it points in the opposite direction. So the field lines have to come out of the positive charge. They have to go back into the negative charge, okay? And that means that all along this equatorial plane or the bisecting plane between the two charges, the electric field must point down, okay? So that's the form of this equation. The electric field is minus 1 over 4 pi epsilon naught sq over r cubed times y hat, okay? Do you have any questions about that? That's from last time. Any questions about that or what the other stuff we discussed last time about the electric field coming out of a sphere? Any questions about that? Okay? All right. So today we're moving into chapter 15. So today we'll talk about the concept of conservation of charge. Okay? We'll do some experiments with Scotch tape. And we'll try to figure out why is it that Scotch tape can, get too sticky and attract to everything and make a mess. We'll talk about polarization of atoms and what that means. And then we will calculate the force between a neutral atom and a point charge. Okay, conservation of charge is this idea. Here's the encapsulation of it. It says the net charge, net means total, so the total charge of a system plus its surroundings cannot change. Now let me remind you how you define a system, okay? When you're doing a physics problem, you get to decide the system. And you draw some imaginary box, and stuff that's inside of your imaginary box is called the system. Everything that's outside of the box is the surroundings, okay? And in every case, your system plus the surroundings equals the entire physical universe. So system plus surroundings. So when we say the net charge of a system plus its surroundings can't change, we're really saying that the net charge of the universe can't change. Okay? So you can move charge around, though. So you can move charge from the system to its surroundings. You can move charge from the surroundings into the system. So for example, this guy here, grumpy guy here, somebody rubbed balloons on his head and positively charged what little hair he has and negatively charged the balloons. So that transferred charge from one place to another, but the net charge of the system plus surroundings didn't change. So if I consider maybe the system to be his hair, right, and the surroundings to be the balloons and everything else, the net charge didn't change, but we moved charge from one to the other. Do you have any questions about that statement, or how that goes? Okay. All right, so let's consider this then. Given that conservation of charge law, can we create or destroy charge? Is there a way to do that? Okay, we've got to vote for no. All right. Can you think of an instance where it kind of looks like charge gets created? Let's maybe analyze one of those cases. Can you think of one of those cases where it kind of looks like charge gets created? Okay. Excellent real-world example. So in a battery, we know that somehow what's going on in a battery, because it's labeled, there's a positive end and a negative end. So it seems like as I use it up, where did the charge go? It's kind of like, it sort of seems like we used up the charge. So somehow it must be that the net charge of the battery plus its surroundings didn't change. We just must have moved some charge around. Okay. So, back here, please. Oh, excellent. Okay, so she's pointing out that there's this matter-antimatter phenomenon where if I get a piece of matter with a piece of antimatter, they annihilate each other, and they almost always are carrying a charge when they do this, right? So there's some neutral particles that can do this, but like you pointed out, an electron with a positron, right? So if an electron gets in the vicinity of a positron, they're a matter-antimatter pair, and they, bam, annihilate each other. And in fact, this is not a rare event. You should know that all around you, inside your body and in all the air around you and in the matter that you're touching, little electron-positron pairs are annihilating all the time. They're also coming into existence. The space is just kind of bubbling with particle-antiparticle fluctuations. And so all the time, there's little electron-positron pairs popping into existence and popping back out of existence again. Just bubble, 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 bubble. So it kind of looks like the universe is creating and destroying charge, right? And in fact, that is going on. When one of these pairs fluctuates into existence, it creates a positive charge and a negative charge. When they bump back into each other again, they do get destroyed, all right? But the net charge of the universe doesn't change in the process. So it is actually possible to create charge as long as you do it in plus-minus pairs. Then you're not violating conservation of charge. Okay? Any other thoughts that we should consider here? All right? So yes, charges can be created or destroyed in plus-minus pairs. And one example is electron-positron annihilation. So you can move charge around, all right, and you can create and destroy it. You just have to do it in such a way that you don't change the total charge of the universe. Any questions? Okay, all right. Now, tape. All right. Let me show you this demo over here. Make sure we got the right one. Okay, and I've got some tape up here to run an experiment and show you some things about how tapes, well, about the electrical interactions with Scotch tape. You're going to get to do a lot of this stuff in the lab as well, and you're going to put numbers on it and make quantitative estimates and all that stuff. So, I see something I need to do first, though. Sorry, I found this note up here. I probably should go ahead and send that. So let me just get that ready to send. I've got some tape up here. And excuse me just a second. Whoa. Tape needs to stay put. All right. But I pull the tape off and stick it on. All right. Does anybody else have this happen to you? That as you're trying to work, sorry, Mom. All right. So, and it's not like it's just the sticky side of the tape that's sticking to me. All right. This is the non-sticky side of the tape that's sticking to me. There is something going on here, right? We'll just set that aside. Hope they can deliver that. All right, so there's something going on, but we can do a little bit of controlled experiments here to try to figure out what's going on with the tape. I took one piece of tape. I'm going to put it on the table as in order to do a controlled demonstration here. I have a second piece of tape, and I'm going to lay it on top of the tape that's on the table. So I have one piece of tape on the table, I have another piece of tape here, and I'm going to put them together because there seems to be something strange that happens when I pull the tape off, right? It happens when I pull the tape off. This thing isn't doing strange things right now. It's as I pull the tape off, something happens. So if I carefully peel off this top piece of tape, okay, it already attracted to me. When it does that, it kind of messes things up. I'm going to see if I can do this again without having it stick to me. All right. I'm folding over one edge of the tape so I can easily pick it up. I still have my reference tape on the table. Let's just try again. And I peel this up, trying carefully not to let the tape get stuck to me. And I want to put it up here on this dowel. All right. So there's a piece of tape that you can see up there on the screen. I want to get a second piece of tape, and I want to see how these guys interact. Okay? The reason I'm using a reference piece of tape each time is so that I'm sure that whatever I did to this piece of tape, I'm going to do the exact same thing to this piece of tape. So I still have the reference tape on the table. I have my new piece of tape. I'm going to put it down, smooth it down, all right? As I'm doing that, right, I'm grounded, okay? As I'm doing that, I'm ensuring that everything here is electrically neutral. And then as I pull it off, interesting things can happen. So here's another piece of tape prepared in exactly the same way as that one. And what we want to watch is what happens when they come together, okay? So you can kind of see up there on the screen what's going on. Okay? Would you call that attraction or repulsion? Yeah, it's repulsion. They're clearly repelling each other. Something's going on. Okay? This is a class on electricity and magnetism, so it's probably something about charges. All right? So if I continue to give myself pieces of tape here that we can experiment with. This is also prepared in the same way. These guys repel, they all repel each other, okay? None of them have attracted each other so far, all right? Now, there's something else weird that happens. Not only do these pieces of tape repel each other, but let me ground myself by touching a piece of metal. Let's see what happens with me, okay? This thing we know is somehow doing some electric interactions, and as I bring my hand close to it, would you call that attraction or repulsion? Attraction. Now, whatever it is pretty short-ranged. It doesn't happen until they get really close to each other. Whereas the tapes, right, one tape with another piece of tape, that wasn't attraction, it was repulsion, and it's actually a lot longer ranged. Whatever this is working at a larger distance than when my hand gets close to the tape, and at very short distances starts to feel an attraction. So what we'd like to do is try to explain what's going on here. So what's going on is that we have charges that are somehow getting redistributed, right? So we're not allowed to change the net charge of the universe, but we can move charges around, or we can create them in pairs. It's unlikely that we're creating them in pairs here. We're just moving them around. And what is likely going on is that the tape here, there's a sticky side. The sticky side of the tape, okay, I'm going to tell you a little bit of chemistry, but I'm not a chemist, so you really should ask your chemistry professor for the full story. But here's the physicist's description of how tape works. The glue part of the tape is made of long, floppy molecules. In general, when something in chemistry is sticky, there's probably long, floppy molecules involved. So the glue part has long, floppy organic molecules involved. And what we think happens is that as I pull one piece of tape off the other, some of those long, floppy molecules break. As they break, sometimes an electron gets caught on one side or the other. Okay? And if the electron gets caught on one side, then you'll end up with a net charge over here and a net charge over here. So if the electron runs to one side, that's your negative charge, leaving behind a positively charged half molecule on the other side. So that's how we think the charges are arising. Now, the electric force must be involved because it's following these kinds of principles. It's acting along a line between the charges. The forces are decreasing with distance. Okay? It also is proportional to the amount of charge, which we could disentangle by using different lengths of tape. All right. Now, I'd like to employ the help of Fluffy here in order to figure out the sign of the charge. So we have over here in the box some silk. and a glass rod, assuming I choose the right rod. Okay? So I'm going to tell you that, in fact, when you rub a piece of silk on a glass rod, the glass rod gets positively charged and the silk cloth gets negatively charged. I'm not going to prove that to you, but I'm just going to tell you that's the case. That as I do this, the glass rod gets positively charged. So we ought to then, with that information, be able to figure out what's going on with the tapes, okay? So supposedly this positively charges the glass rod. And now if I bring this over here, I ought to be able to tell what happened to the tapes. Okay? All right. So what kind of charge do you think is on the tapes? Positive, okay, because they repel. Now, presumably, to finish the experiment, it must be that the silk is getting negatively charged. Of course, the silk is in kind of a weird configuration here, but hopefully this will work as well, just to finish it off, that the silk has a little bit of attraction between these guys. Of course, the silk is a more complicated geometry. So, all right, so we know that whatever's on these tapes is positive charge, okay? Why does it get charged is a chemistry question. We think it's due to breaking large molecules, which transfers ions, so that, or it doesn't really matter whether you think about transferring the electron or transferring ions. It's some net charge that gets, it's some charge that gets redistributed. Now, why does it end up positive or negative is actually a complicated question, because it's going to depend on surface science. And if you've thought at all about surface science, that's actually a very complicated thing. You have all the chemistry interactions that are happening among the constituents of the surface, and then you have the fact that you've got dangling bonds, and then you have to worry about, are you in air or are you in water? Well, what kind of air? What kinds of dirt and dust has already settled on the surface? It's a very messy question, which is why answering whether it's positive or negative is a current topic of research. So to predict that, yeah, charge will happen as I pull along floppy molecules apart, that one side will get charged and the other side will get oppositely charged, that's just the breaking apart of those long floppy molecules. But to tell which way the charge is going to go is actually difficult and a current topic of research. So we think we understand then why these tapes would repel each other. Okay, the positively charged glass rod told us that these tapes must be positively charged. Actually, when they sit here a while, the charge leaks out, so let me recharge the tapes. And I do that. I have my reference tape on the table, and I pull off the top tape and hang it up. Oh, yeah, and of course, when it touches me, it kind of messes things up again. So let me recharge this guy, too. Got the reference tape on the table. Pull this guy off, trying not to let the tapes touch me too much. And we'll recharge this guy. Again, using the same reference tape, and then when I smooth it down, presumably that grounds everything, and then I pull it off again, that's when the charging happens. Oh, and I'm trying to not let them touch my hand. As they touch my hand, that messes things up a little bit. All right. Okay, so I should have positively charged pieces of tape, and that explains why they're repelling each other, okay? And this should be then a force law that goes like 1 over r squared, right? Charges interact with each other with 1 over r squared force laws. Now, we have something else to explain though, right? I mean, something also happened. I'm going to ground myself first. This is a positively charged tape, and somehow when my hand comes in, there's something else that goes on. There's an attraction. We need to explain this as well, okay? And it's not that I'm charged. I'm grounding myself, okay? So I'm neutral. I'm holding a piece of metal back here, and then somehow there's something that happens. So we need to understand that as well. Do you have any thoughts on what's going on here? Yeah. Okay, so maybe what's going on is that I'm electrically neutral, and I made sure of that by touching pieces of metal back here, which grounds me and makes me electrically neutral. And then, but my hand is made of particles, right? So I have electrons in my hand, I have protons in my hand, I have neutrons in my hand. And maybe what's going on is that as I get close enough, the electrons in my fingertips run closer to that positive charge. And then they get attracted to each other by doing that. Okay? All right, so let's explore that idea. Okay? So let's think about a simple atom, right? We're all made of complicated atoms and complicated molecules, and the principles will follow to those complicated situations, but it helps to think about the simple case first. So let's first think about a hydrogen atom. So a hydrogen atom is made of a proton with an electron. The proton is very small. It's positively charged, of course, sitting in the nucleus. And the size of that nucleus is about 10 to the minus 15 meters, about a femtometer. And there's an electron swarming around it. I've drawn it in the 1s state here. Okay, the 1s state is spherically symmetric, so I'm drawing the one electron as zooming around so as to make kind of a fuzzy ball of charge around the atom. And the extent of that ball of charge is about an angstrom. So the charge of the electron cloud equals that of the nucleus. So this is a total neutral atom, right? Hydrogen atoms are neutral. And if the electron cloud is centered on the nucleus, then how should I think of this? So let's think here. I want to think about what's the electric field out here. What's the electric field out here? One thing I should think is that the positive charge at the center, the proton, exerts an electric field like a point charge. The proton isn't quite a point, but we're far enough away that it may as well be a point. So the proton exerts an electric field over here like a point charge. What about the electron cloud? What kind of field is it exerting over there? Yeah, it's similar to a point charge. So this electron is in a ball shape. We saw that a spherical set of charges gives an electric field outside of the sphere that looks like there's a point charge. So if I'm sitting over here, then the electron itself is also putting out an electric field that looks just like there were a point charge sitting at the center of the atom. So altogether then, those two electric fields should cancel. And in fact, they should exactly cancel because this electron cloud is spherically symmetric. So there must be something beyond that. And what happens is that, so here's the atom. Let's take the hydrogen atom again. Proton in the middle, electron cloud around it. And what I want to do is think through what happens when a positive charge comes near. We saw that our tapes are positively charged. So let me pull in a positive charge from the left and just think through what happens to this atom. Okay, so I pull in a positive charge, it applies an electric field, and the electron cloud basically gets attracted to that positive charge. So here's the positive charge. The electron cloud is a little bit attracted to it and shifts over, which means that the center of the negative charge is moved a little bit. Okay, I'm going to say that the proton didn't move all that much because it's so much more massive, but the electron cloud moved a little bit closer. And so the atom, what we say is that the atom developed a dipole moment, right? There's now a dipole moment here. I'm going to abstract this a little bit more and say that, well, since the electron is a cloud, then I'm going to, from a distance, I'll consider that to be like a point charge at the center of the cloud. Okay, because from far enough away of that ball of charge, I can treat it as that point charge. So here's the point charge associated with the center of the electron cloud. Here's the point charge associated with the proton. And this is an abstraction. It's an approximation, but it's a good approximation if you're far enough away. So the atom acquires a dipole moment, right, in this case. We call that an induced dipole. So it's not a dipole that's permanent. This is a dipole that's caused by this positive charge coming near the atom. If I take the positive charge away, there won't be a dipole moment to the atom anymore. Do you have any questions about that? Yeah? Is it necessary that they get positively charged? Could they have become negatively charged? Okay. So in fact, okay, that's a good question. I'm sorry I missed your question before. Thinking back to the tape, if I think that, so it's a good question. Basically, you know, can I make some negatively charged tapes as well? So here's a way to do that. If I want to make a negatively charged tape. So and I'm going to put down 2 pieces of tape on the same reference spot, right? And so what's happening is that as I pull 2 pieces of tape apart, these have all been top tapes. So the top tape is getting positively charged. If I could create a bottom tape, it should get the other part of the charge. It should get the negative charge. So in fact, you're asking a great question. Let's just see if I can set that up. So what I'm trying to do is I put down 2 pieces of tape, and I'm pulling off the 2 pieces of tape together. I'm grounding myself, okay, and then I'm going to rub the backs of them just to make sure that there's no net charge on this guy, right? As I pull this up, it should have become net positive charge, but I'm going to try to get any of that charge to come off. All right, so now as I carefully pull these guys apart, I should be able to then, since I have 2 pieces of tape, the top one, which is this guy, gets positively charged. The bottom one should become negatively charged. I'm really glad you asked that, actually. So let's see if all that actually works. I didn't try this ahead of time, so hopefully it works. So presumably the top one is positively charged. Okay, of course these guys have kind of probably had their charge leak out a little bit. There we go, that's positively charged. This guy's supposed to be negative. I hope it works. Oh, you don't have the screen up. All right. All right. So this guy's, oh, it touched me. Okay, this guy's positively charged. This guy should be negatively charged. Let's hope it works. And ha, physics works. All right. Very cool. That was an excellent question. Thank you for asking that. Does this address what you were talking about? Okay. All right. So it's a great point, which is that the top tapes that come off are positively charged. They must be leaving behind their pairs, right, since we have to conserve charge. Excellent question. All right, any other questions before we go on? Thanks for asking that. I think this one was our negatively charged tape, so I'll put that up there just in case we decide we need another negatively charged tape. Good, thanks for the question. Okay, so we've induced a dipole in the atom by bringing a charge nearby. So we induce a dipole. Induce just means that we cause that dipole to happen by applying an electric field. When we take that electric field away, the dipole will go away. So that's an induced dipole moment. And it's quit responding. There we go. All right, so that's a dipole moment. We'll treat it now like two-point charges a particular distance apart. So we'll treat that polarized atom like a dipole moment, which is a point charge with a paired point charge, positive and negative charges, a particular distance apart, s. Then the dipole moment P is Q times s. Do you have any questions about the definition of a dipole moment? All right, and also keep in mind that we caused this dipole moment by applying an electric field to an atom. So what happened here, as you guys have already pointed out, what happened here was that the positively charged tape induced a dipole moment in my hand. The electrons were attracted, the electrons in my hand were attracted to the positive charge on the tape. Those electron clouds shifted towards the tape. They exposed then some positive charges on the other side and created little dipole moments. Okay? Now, just to think about orders of magnitude here, we shouldn't think of it as though, you know, there's a ton of electrons just sitting on the tip of my fingers and I have exposed protons back here. It's a much smaller shift than that, okay? So if this is the size of the ball of charge that's surrounding an atom, and if this is the metal, it's a very slight shift, okay? But it's enough to have a measurable effect. So the way that we do clicker questions in this class is first I give you time to answer by yourself. That's very important that you go through your own line of reasoning and make your own choice. Then I'll give you time to discuss with your neighbor. Then we'll discuss all together. All of that will happen before I grade the question. So you have plenty of time to get the right answer. So here's the question, and answer first by yourself. Atom A is easier to polarize than atom B. Which atom would experience a greater attraction to a point charge a distance r away? You can assume throughout the problem that this plus and minus charge are the same magnitude as this plus and minus charge. It's simply going to be that the distance between these guys can be different. And I'll keep these atoms centered where they are so that this distance r is the same throughout the problem. Okay? So atom A is easier to polarize than atom B. Which one experiences a greater attraction to a point charge a distance r away? Answer first on your own. All right, with 200 answers in, go ahead and discuss with your neighbor. Convince your neighbor that you're right. Ready? Okay, all right, so what are some lines of reasoning we should consider? And again, when we do these clicker questions, I'm interested in drawing out the logic, okay? I'm not so interested in, hey, this is the right answer, and we move on. I want to know the lines of reasoning that we need to use, because what's going to happen to you on the test is you'll get to the test, you'll have your brain will present to you a few lines of reasoning. You need to be able to figure out which one is the correct, which one is logically correct. So tell me some lines of reasoning we should consider here. Which atom is going to experience the greater attraction? Yes, please. Okay, all right. So what he's saying is that we have an equation for the electric field of the dipole. So you're going to think in terms of that. And you're saying that this dipole, once it arises, is putting out an electric field. And that electric field is proportional to the dipole moment. And the dipole moment is proportional to this distance between the point charges. And so this guy, since it's got a larger dipole moment, it must have a larger electric field that it exerts. Did I get it right? Yeah. OK. All right. Other lines of reasoning we should consider? Yeah, because there's several ways to think about it. Yeah, go ahead. OK, so another way we can think about it is that it's like there's more. So if there's a stronger dipole moment, maybe we need to think that there's more charge. And then if there's more charge around, there should be a stronger force going on. OK? All right. Other lines of reasoning we need to think about? OK. All right. So let me repeat that for the people in the back. This line of reasoning was that for atom A, it's easier to polarize, so it develops a larger dipole moment. But a way you can think about that is that the charges moved more. So this positive charge got much closer to this negative charge over here. And they're going to then be the dominant attraction. Is that basically the line of reasoning? OK? All right. Good. So we got out a lot of lines of reasoning here. And there are different ways to look at these things, okay? So that's often the case in physics, that a few lines of reasoning will be a few different ways to get to the answer. As long as you're making logical steps that are correct, you will get to the correct answer. So one way to think about it is that if atom A is easier to polarize, it puts out a stronger electric field, right? And so then that stronger electric field will cause a stronger force. I can also just think very simply. You can always do these problems intuitively by going back to point charges, right? We built up that dipole electric field from point charges anyway. So if I think in terms of the point charges, this point charge moved a lot more than that one, and this one is then a lot closer to the negative charge that's inducing the dipole moment in the first place. So this will have a pretty strong interaction. So both of those lines of reasoning are correct. They both lead us to the answer that atom A is going to experience the greater attraction to this point charge. Do you have any questions about that? All right. So atom A experiences the greater attraction, the greater force. All right. This brings up the idea of polarization, polarizability. What we saw was the idea that different atoms, because they're chemically different, will respond a little bit differently to an applied electric field. So the idea is that I apply an electric field to an atom, and the electron cloud shifts relative to the nucleus. This polarizes the atom, but how much is it going to respond? How much it responds is going to depend on, well, the strength of the electric field, right? A stronger electric field applied will give me a stronger response, that's for sure. But how much it responds also depends on the type of atom. Certain atoms are easier to polarize than other atoms just due to their chemistry, or perhaps due to the molecule that they're sitting in. So the polarization has to depend on both of those. That is, the response has to depend on the applied electric field. As the applied electric field gets stronger, the response is stronger. But also there's something that's just a material property that tells me how much this atom gets polarized. Now, the other piece of information I need to tell you is not only can we define something called a polarization, which has a vector that's aligned with the applied electric field, and so then the polarization is alpha times the applied electric field. This polarization is the same thing as the dipole moment that forms. So that induces a dipole moment in the atom. This P is equal to that P. They are the same. Polarization induces a dipole moment, which is equal, okay? And alpha is just a material constant. There are lookup tables for it. There are ways to calculate it. We have ways to measure it. They mostly agree, okay? So they agree to several decimal places, so we think we understand that. So in an induced dipole, though, right? So the dipole moment itself is QS, right? If I apply a field to something that's polarizable, a polarization develops. That polarization P is equal to the dipole moment. In an induced dipole, is the distance between the charges fixed, though? So if I apply a field, I induce a dipole, is the distance between the charges fixed? No, it's got to depend on this applied field, right? So the higher the applied field, the larger that distance between them. All right, so what I want to do now is just calculate that force. We have enough information on hand now to calculate the force between a point charge and a polarizable atom in its vicinity. So let's calculate that. Step one, so this diagram goes as follows. On the right-hand side, I have a point charge, Q1. When I'm doing these problems, to make it intuitive to myself, I always pretend that the charge I write down is positive, okay? The equations are general and will also work for a negative charge, but for the purpose of reasoning it out in a physically intuitive way, I like to think of a positive charge here. So there's a point charge here. It's a distance away from an atom, okay? So here's an atom, and we're going to say that the center of the atom remains fixed, okay? So fix the position of the point charge, fix the center of that atom. All I want to see is what happens as the atom then responds to the electric field that's applied to it. So these are a particular distance r apart. Q1, charge 1, exerts an electric field throughout space. We know what that looks like for a point charge. E is 1 over 4 pi epsilon naught, Q over r squared times r hat. That means there's an electric field right here exerted on the atom that's of this form. Okay, I'm going to call that E1 because it's exerted by Q1. Do you have any questions about that so far? Okay, so step one, think about this point charge applying a field on the atom. Step two is that the atom responds by polarizing, right? Anytime there's an applied electric field, okay, the applied electric field in this case is this direction. Positive charges tend to move along the electric field. They tend to follow that arrow. Negative charges tend to move the other direction. And so this positive charge, the positive and negative charges separate a little bit, and the electron cloud shifts a little bit towards the charge over here. So the field polarizes the atom. Okay, I already gave you that equation for polarizability P. Polarizability P is alpha times E1. I don't know what alpha is. It's going to depend on the atom we're given. But the polarization is proportional to the electric field that's applied. The electric field that's applied, though, we know, right? We know that the applied electric field was the point charge electric field. That's 1 over 4 pi epsilon naught, Q1 over r squared. So I actually know what this P is. And I know that that P I can also think of as the dipole moment, right? That polarization is the dipole moment. Questions so far? Okay? All right. Now we've got so much information up here that I want to also give you the summary slide, okay? We didn't go through this whole slide yet. We're going to go through a few steps. We're right now on step 3, but here's step 3, okay? So there's the summary slide, and we're going to work through it step by step. So step 3 is that now I want to think of that induced dipole moment. Well, now that this atom has responded by having an induced dipole moment, it's exerting a particular electric field now, right? It wasn't before. I'm assuming that I had something like a hydrogen atom where when it's neutral and it's not polarized, it's not exerting an electric field. When I shift the electron cloud relative to the nucleus of the atom, now there's a dipole electric field that's being exerted. So the induced dipole is exerting now an electric field throughout all of space. What form does it take? Well, we know what the dipole electric field is. I've oriented, the dipole gets oriented, of course, along this line connecting the atom and the charge. And I want to think about the electric field back here. The electric field back here, well, that's on axis. So we have an equation for the electric field of a dipole along its axis. It's this, 1 over 4 pi epsilon naught, 2p over r cubed, where p, I don't think I've put the p there before for you, but we typically have put qs, right? So qs is what you're used to seeing there, and yet qs is the dipole moment, which is p, and that dipole moment is also this polarization alpha times E1. Okay, do you see that connection? So now, in place of p, I'm going to put alpha E1, and E1 is that equation for the point charge, right? The electric field of a point charge. So right here, I'm writing the electric field of a point charge. Notice that all of a sudden, I've got a lot of r's running around, right? The electric field that this dipole puts out falls off like 1 over r cubed. A point charge's electric field falls off like 1 over r squared. A dipole's electric field falls off like 1 over r cubed. And now I have both of those powers in here, because it's the electric field of a dipole, which falls off like 1 over r cubed. But this dipole moment depends on the applied electric field, and the applied electric field falls off like 1 over r squared. Do you catch that? How many powers just showed up? Okay. So altogether then, I have 5 powers of r in the denominator. If we put all this together, I get 1 over 4 pi epsilon naught squared. The 2 comes straight down. The alpha comes straight down. I have a q1. R cubed times r squared is r to the 5th. So the electric field put out by an induced dipole moment that's due to a point charge in its vicinity falls off like 1 over r to the 5th. Okay, do you have any questions so far? Okay, so that's the field put off by this guy. This dipole moment is exerting an electric field E2 on the point charge, and we can calculate the force associated with that. So this E2 represents that electric field due to the induced dipole. E2 times Q1 gives me the force. So now we finally have a force, right? I wanted to calculate the force. Here it is. Force is Q1 times E2. So there's the Q1 times E2 we had already calculated. So I just need to take this equation, 1 over 4 pi epsilon naught squared times 2 alpha Q1 over r to the 5th. Take that equation and multiply by Q1. That gave me the force. So this is the force on Q1. But equal and opposite forces says that it's also the force on the atom, right? They are exerting an equal and opposite force on each other. Okay? So the force that the charge exerts on the atom is the same as the force that the atom exerts on the charge. They're just equal and opposite. Okay? Do you have any questions about that? Okay? And here's a summary of all those steps. At the end of the day, we got that the force between a point charge and an atom goes like 1 over r to the 5th, because it's incorporating the dipole's electric field, which falls off like 1 over r cubed, and it's incorporating the point charge's electric field, which falls off like 1 over r squared. Altogether, it gives me 1 over r to the 5th. So that's fast, okay? In fact, if you haven't done it yet, get yourself a plotting program and plot out what 1 over r squared looks like, because we know the point charge's electric field falls off like 1 over r squared. We know that a dipole electric field falls off like 1 over r cubed. Okay? Now we know that the force between this point charge and a polarizable atom falls off like 1 over r to the 5th. That's really fast. And that explains why, yeah, these are charged, okay? And so I have the tapes that are charged. Okay? Maybe they're still charged. Sometimes on a humid day they don't remain charged. But the two positively charged tapes repel each other, and they repel each other at a pretty good distance, because these guys should be following a 1 over r squared law. Okay? Now when I think about my hand, should my hand follow a 1 over r squared law, or a 1 over r cubed law, or a 1 over r fifth law as far as the force between my hand and that piece of tape? 1 over r to the 5th, because my hand's going to get polarized. So that explains why my hand has to get a lot closer before these guys start feeling that attraction. Okay? So polarizability is present, it's just a very short range thing. So that gives us the force on the point charge, between a point charge and an atom. And, oh, there we go. There was our summary slide of what we did today. All right, we're done for today. I'll see you guys on Monday.
My favorite way to heat up a leftover burger, or any food for that matter, is to use a microwave oven. But have you wondered, how does it work? How does it heat up things without fire? Well, it turns out that these ovens produce electric fields. And burgers, or any food items, contain moisture, which have water molecules. And these water molecules are electric dipoles. But wait, how does that explain anything? For that, we need to investigate what happens when dipoles are kept inside an electric field. And that's exactly what we're going to do in this video. And towards the end of it, we're going to figure out exactly how a microwave oven works. So let's begin. So let's say we have a uniform electric field inside which we keep an electric dipole. And just to quickly recap, what's an electric dipole? Well, two equal and opposite charges separated by some distance is a dipole. And what is this P thing? Well, remember, dipoles in themselves create this beautiful electric field, and the strength of the field everywhere depends on the product of the charge and the distance between the charges. And that product is what we call P, the dipole moment. The dipole moment represents the strength of the dipole. And why is it from negative to positive charge? It's a vector. Why is it this way? Because it kind of represents the direction in which it creates the field. You can see the field that dipole creates is away from the positive, and it's coming into the negative, and so the dipole moment kind of represents that. Now, we've talked a lot about this in our previous videos, so if you feel you need a refresher, feel free to go back and check that out. But we don't have to worry about the field created by the dipole in this video, so don't worry about that. My question to you is, what's going to happen to this dipole when I keep it inside an external electric field? Think about the forces that are going to be acting on this dipole and see how the dipole may be moving. So can you pause the video and think about what would happen? All right. So I know positive charge experiences a force in the same direction as the electric field. And so it's going to get pushed this way. And negative charge experiences a force in the opposite direction of the electric field. And so it's going to get pushed this way. And since the two charges have the same strength and it's in the same electric field, the two forces will be exactly equal and opposite. And therefore, I know the net force acting on the dipole, or the total force acting on the dipole, is 0. So this means what happens to our dipole? Well, our dipole is not going to accelerate. So if it was at rest, it's going to stay at rest. It's not going to move. It's going to stay over here. But because the two forces are acting at two different points, we can kind of feel it in our bones. This is going to make it turn. Think about it. Imagine these were strings attached and you pull it. What's going to happen? It's going to make it turn. You can feel that, right? It's going to make your dipole turn this way. And this turning effect provided by the force is called a torque. So although there is no net force acting on it, there will be some total torque that acts on our dipole. And in a future video, we'll calculate exactly what that torque depends on, and we'll derive an expression for that. But for now, let's see the effect of that torque. So the torque is going to make our dipole turn. The two forces are going to make it turn. And what I want to know now is, will the dipole keep turning forever? So what I want to know now is, as the dipole turns, what happens to this torque? Does it stay the same? Does it increase? Does it decrease? Will its direction change? What would that depend on? So for that, we need to know a little bit about what does torque depend on. Well, torque definitely depends upon the strength of the force. If the forces are larger, we'll have more torque. But the torque also depends upon the distance between the two forces. So torque also depends upon this distance. If this distance is high, if this distance is far, if the forces are farther apart, torque is high. It's for the same reason when you look at a bicycle, the bicycle handles are far apart from each other, because when you put a turning force on them using your hands, these are the hands, okay? the forces are far apart, and so the torque becomes very high. It becomes easier to turn the handle. But imagine if this handle was not there, okay? And then you had to apply that same turning force directly on the rod. Now the forces would be so close to each other, the distance would be very small, the torque would be very small. It becomes so difficult to turn this. You can feel this, right? So torque also depends upon the distance between the two forces, and I want you to think about that. As the dipole turns, what happens to the distance? Will it increase, decrease, stay the same? So pause the video and think about it. Let me get rid of this epic drawing. Okay, let's see. A second later, our dipole is going to turn, and the forces come closer to each other. Can you see that? The distance between them has decreased. Ooh, so this means as the dipole turns, this torque becomes smaller. And the more it turns, the closer the forces get. The strength of the force stays the same, but the torque becomes smaller and smaller. Eventually, the dipole gets perfectly aligned, and the forces are also along the straight line, so the torque goes to 0. But now there is no torque. Now these forces are just pulling the dipole apart, not producing any turning effect. So now our torque has gone to 0. So I'll just delete that. And so long story short, what happened? Let me go back. When the dipole is not aligned, like when it's now perpendicular to the field, the torque acts until it gets aligned. Now in reality, even though right now the torque is 0, as it turned, it gained momentum. It gained some speed. And so because of its inertia, it might overshoot a little bit. And now I want you to think, what if it overshot this way? What would now happen? Well, now again there will be a torque, but this time look, the torque would be in the opposite direction. Ooh, so again we're seeing that the dipole is trying to get aligned in the direction of the field. So again, the moral of the story is dipoles experience a torque that aligns them or tries to align them in the direction of the field. So let's quickly check our understanding. What if I have an electric field to the left and I kept a dipole this way? What direction will be the torque? Clockwise or anti-clockwise? And how will it align? Can you think? Okay, since P tries to align towards E, this time the torque will be anti-clockwise. And once it aligns, the torque disappears. Let's try one more. What will happen over here? Okay, again, P wants to align towards E, so this time the torque will be, clockwise. Again, once it aligns, torque disappears. One more. How will the torque be? Again, P tries to align towards E, and so this time the torque will be again anti-clockwise. Once it aligns, torque disappears. Okay, now let's really start having fun. So again, keep a dipole in electric field, torque acts on it until it aligns, right? And it overshoots because of its inertia, but the torque takes care of it and aligns it. Now here's my question. What if as the torque acts, as it overshoots, before it has time to align, I flip my electric field? What happens now? Well, now the dipole says, okay, again I have to align, so it'll continue to turn. And again, before it has time to align itself, and when it overshoots, what if I flip my field again? What's gonna happen? Ooh, can you see what's happening? If I flip my electric field at the right time, I can keep that dipole turning. And that's exactly how your microwave ovens work. So what do microwave ovens do? Well, they produce microwaves, of course. But what are microwaves? They're electromagnetic radiation. We'll talk more about them in the future videos. But what's important is that these microwaves contain flipping electric fields, and they're actually flipping at billions of times per second. And when you keep any food item inside your microwave, pizza, burger, anything at all, you'll find that these food items always have some or the other moisture, which means water molecules, not so giant ones, but tiny water molecules. And the important thing is these water molecules are electric dipoles. And you'll learn more about this in chemistry. It turns out that oxygen and hydrogen are sharing electrons, and the shared pair of electrons are pulled more towards oxygen compared to hydrogen. As a result, oxygen becomes slightly negative, hydrogen becomes slightly positive. We have a dipole. Turns out that this dipole moment is very, very tiny, but that's all that we need. That tiny dipoles, these tiny dipoles, when they come inside a flipping electric field, they will keep turning. And as they turn, they will hit other molecules, they will make them vibrate. Pretty soon, all the molecules are jiggling, and as a result, your burger is gonna get hot very, very quickly. This is how microwave ovens work. Incredible, isn't it? To think that we use the idea that dipoles turn inside electric fields, and we can use that to heat up food. That is mind-boggling for me. It's pretty amazing if you ask me. So, long story short, keep a dipole inside a uniform electric field. We'll find that the total force acting on it is 0, so the dipole will not accelerate, but there will be a torque acting on it. And what does the torque do? It will always try to align the P vector or the dipole moment in the direction of the electric field.
So there is some pretty random location of 4 charges. Now, what's going to happen if we have minus charges here and here, plus charges there and there? Well, the first thing that's going to happen is that the charges are going to feel their closest neighbors, and a plus is going to be attracted to a minus. So the very, very first thing that's going to happen very quickly is that the plus and the minus are going to get pulled towards each other, and we're going to end up with a situation like this. And these two are going to feel each other, pulled towards each other. And so really quickly, we're going to end up with a situation like that. And at that moment, we have 2 dipoles. So we started with 4 charges at 4 random places. And very, very quickly, by the Coulomb attraction, we end up with 2 dipoles. And this is the generic thing that will happen unless you make some very special arrangement like a square, for example, where something different will happen. So right now, I have 2 dipoles. Each one of these has electric fields. They look something like the fields that we drew over here, but on a smaller scale. So there's white field lines between these 2 and around these 2. There's white field lines between these 2 and around these 2. And now I have 2 dipoles. And what we are going to learn to understand today is what happens next. What are the forces between the dipoles? How do they interact with each other? What do they do? Okay, so now we ask ourselves what's going to happen in a situation like this. We have these 2 dipoles. The electric field from this dipole is going to exert a torque on this one, making it turn. And the electric field from this dipole is going to exert a force on this one, making it turn. We're going to do the calculation later. We will see how electric fields make dipoles turn. We'll see how dipoles themselves make electric fields. You can already see that. We already saw that. This dipole is making a field. Each of these dipoles is making a field, and we'll see later the math that will show us that a field makes a dipole turn. So what's going to happen is that this dipole is going to turn, and we'll end up looking like this. And this dipole is going to turn, and we'll end up looking like this. And the dipoles will turn until they're aligned. So first the dipoles formed very quickly, then more slowly, each torques the other, and they turn until they're aligned. And then even more slowly they attract each other. Once they're lined up like this, there's a weak force. Even though this is neutral, and even this is neutral, they have electric fields. These neutral objects have electric fields that look like the electric field of this. And the field of this one will pull on that one, and the field of this one will pull on that one. Very slowly, more slowly than the time it takes for them to torque and align, they will attract each other, and at the end, we'll end up with a configuration of 4 charges that looks like this. A positive, a negative, a positive, a negative, and a positive. So the math that we need to do now, we need to understand the field that a dipole makes. I showed it to you here. We then need to understand how an electric field created, however it's created, makes a dipole turn in a certain way. And then we need to understand how an electric field pulls a dipole, not with anywhere near as strong a force as a naked charge would, but pulls a dipole so that 2 dipoles can pull each other together, and at the end we end up like this. So why might you be interested in this? Well, this is at a cartoon level, in a very simplified level. This is what happens with atoms and molecules in your body and in the world around us. Every water molecule is a dipole. So when I talked about the forming of the dipoles, that could have been forming of water molecules. Now, it's true that the molecules I used here had only 1 positive and 1 negative, whereas water is 2 H's and an O, so water is a little more complicated than this. Maybe this is something like CO, carbon monoxide. So the first thing I described was the formation of the COs. Then they felt one CO felt the presence of another, they lined up, and then they attracted each other, and we ended up with a larger molecule. So you can think of these electric interactions between dipoles as being the very beginnings of chemistry. Chemistry there's much more to chemistry than just dipoles, but this is the beginnings, this is the germ of chemistry. This is the very beginnings of chemistry. And more generally, this is the beginnings of how charged particles behave in any real situation, because they're never isolated. There are always other charges around. The first thing that happens always is you form dipoles, and then the dipoles interact. You can get more complicated structures than this. There's more to the world than 2 pluses and 2 minuses. For example, maybe you'll have 2 of these objects. So here's a second one. There's a positive charge, and there's a negative charge, and there's a positive charge, and there's a negative charge. And we could now start asking, what's the field of this object? What's the field of this object? How do these 2 interact with each other? Do they turn each other? Do they attract each other? We could start looking at the attractions between more complicated objects still, with different shapes. In 802, we're only going to go as far as the mathematics behind dipoles, how dipoles, what their field is, how they interact with each other, how they torque each other, how they pull each other. But I want you to understand that this is the beginning of a journey which leads you from simple elementary objects with 1 plus or with 1 minus to dipoles, then to several of these, then to more complicated objects. This is the beginning of a journey to understanding how complex forms of matter emerge from simple underlying laws, like the laws of electricity and magnetism.
When you keep a dipole inside a uniform external electric field, the charges experience equal and opposite force, and so the dipole as a whole experiences a net 0 force. But the 2 forces makes the dipole turn. In this case, it'll tend to turn it this way, and as a result, there will be a torque acting on it. And what does that torque do? Well, it'll always try to align the dipole in the direction of the field. Let me show you. If you have the field to the left, and let's say you keep a dipole this way, the torque will act in a way to try and align it. And once it's aligned, the torque disappears. And it doesn't matter how the field is, the torque will always try to align the dipole in the direction of the field. And this is something we've seen before in the previous videos. And so if you need a refresher, feel free to go back and watch our video on intro to torque acting on dipoles. But what we're gonna do in this video is figure out how much that torque is in terms of the dipole moment and the electric field. So let's do that. So how do we calculate torque in general? Well, if there are two equal and opposite forces acting on any object, we call that as a couple, then the torque due to that couple always equals the strength of the force. The forces are equal, so strength of the force multiplied by the perpendicular distance between them, which I'm calling as L. And over here, L would be this distance. This is the perpendicular distance, right? This is our L. So now we need to find what this force is and what this length is in terms of what? In terms of the electric field strength, in terms of the charge, and the length of the dipole. So let's put all of that. So let's say the charge is Q, and the length of the dipole is, I don't know, let's call that as D. Sometimes in textbooks we call it as 2A, but it doesn't matter. You can take any variable you want. So let's see, can I calculate what the force is? Well, yeah, I know the charge, I know the electric field, and from that I can figure out what the force is. And similarly, I know this length is D, that's the length of a dipole. And if I know this angle, and you can assume that angle to be say theta, then from trigonometry you can figure out what the length is. Ooh, so we can simplify, and I want you to pause the video and see if you can simplify this yourself. You have everything that you need. So pause and give it a shot. Don't worry about going wrong, it's fine, but always try to first do things yourself. All right, so let's start by figuring out the force. How much is the force? Well, for that, I look at the electric field. What is the, remember what is the meaning of electric field? It represents the force acting on 1 coulomb. So if I keep 1 coulomb, the force is E. If I keep 2 coulombs, the force is 2E. So if I keep Q coulombs, the force would be Q times E. So from the definition of the electric field strength, I know the force is going to be Q times E. So that's our force. Okay, now how do I figure out this length? Well, for that, let's take this angle to be theta. This is the angle between the dipole moment vector and the electric field vector. And now from this right angled triangle, I know the hypotenuse. I want to figure out what the opposite side is, and so I can use sine theta. So sine theta is going to be L divided by D. So L equals D sine theta. Yay, we found that as well. So let's write that. This is going to be D times sine theta. Okay, can we simplify this even further? Oh, yes, we can. I see something. Do you see it as well? Q times D, we've seen that before. What do you call the product of the charge and the length of the dipole, or the distance between the two charges? Hey, that's our dipole moment. Remember, that represents the strength of our dipole, and we call it P. So Q times D is P, and we have E, and so we get P times E times sine theta. And I think we're done. We're actually almost done, not completely, because this represents the magnitude of the torque. But remember, torque is a vector quantity. It has a direction as well, which means we should be able to write this as a vector equation. But how do we do that? Well, I look at the right-hand side and I say, look, I have two vectors. P is the dipole moment, which is given by this vector from negative charge to positive charge. That's a vector. And E is the electric field vector. So I have two vectors being multiplied. So that means we're talking about vector multiplication. And then we have cross products and dot products. And sine theta comes under cross product. That's the vector product. So what I'm trying to say is that we can now write that the torque vector, we can now write it as P cross E. P cross E. Because the magnitude of P cross E is P sine theta. But wait a second. If you remember vectors, you might also say, wait a second, but can't it also be E cross P? Because magnitude of E cross P is also EP sine theta, which is the same thing. The difference between them is in the direction. P cross E and E cross P are in the opposite directions. So the question is, which one is our torque? Should I write it as P cross E or E cross P? How do I figure that out? Well, P cross E represents P turning towards E, and E cross P represents E turning towards P. But in our case, it's the P that's turning towards E, right? So we will not write it as E cross P. We will write it as P cross E. That represents the true direction, and there we have it. This represents our vector equation for torque. So in our example, what is the direction of the torque? Well, we could say the torque is in the clockwise direction, but we need a particular direction for the vector, right? So for that, we use our right-hand thumb rule. We use our 4 fingers. We make sure our 4 fingers are in the clockwise direction, whichever direction the P is turning. And then the thumb represents the direction of the vector. And so in this case, we say the torque is into the screen. Let me give you another example. Let's say this time we have a dipole whose dipole moment is to the left, and we have electric field coming out of the screen. Now tell me, what direction will be the torque acting on it? Can you think about it? Well, again, torque is P cross E, which is basically saying that P will get aligned towards E. Now over here, it's a little hard to visualize, but E is coming out of the screen. So it's a little hard to visualize that. And therefore, P is gonna turn like this. And so what will be the direction of the vector, of the torque vector? Well, again, we use right-hand thumb rule such that our 4 fingers represent this turning. And so for that, it'll be this way. And so now thumb points upwards. And so we'll say torque is pointing upwards. That's the direction of P cross E. So that's how you get the direction of the torque. My final question to you before we wrap up is, for what angles do you think our torque is going to be maximum? And for what angles do you think it's going to be minimum? Can you pause and think about that? Okay, for that, I'm just going to look at the magnitude. And since I'm only considering the angle, for what angle is sine theta maximum? Well, sine theta is maximum at theta equals 90 degrees. So that means when the angle is 90 degrees, that's when I get maximum torque. So your P should be perpendicular to the electric field vector. And that kind of makes sense because when P is perpendicular to E, the two forces are farthest apart. And that's why, so the L will be maximum. And that's basically the reason why our torque would be maximum. So the maximum torque over here. Fine. When do you think our torque would be minimum? The minimum value would be 0. And that is when sine theta becomes 0. That can happen when theta is 0, meaning P and E are aligned, somewhat like this. And that kind of makes sense because in this position, the two forces acting on the two charges are kind of like pulling the dipole apart, not producing any torque. The torque is 0. And this is something we've seen before as well. The whole idea is the torque is trying to align the P in the direction of E. And once that has happened, the electric field is happy, everybody's happy, torque goes to 0. But there is one more position in which torque can be 0. That is if theta is 180 degrees. Because sine 180 degrees is also 0. And that would look like this. So this is where P, this is P actually inverted, okay? P and E are exactly opposite to each other. Why is the torque 0 over here? Because if you look from the forces point of view, notice even here we have, on this charge there's a force like this, on this charge there's a force like this, and that's not producing any torque. And as a result, you get 0 torque. So in both these cases, we have no torques. And therefore we can say in both these cases, well, our dipole is in equilibrium. Equilibrium is a state where net force and net torque is 0. Now, net force is 0 in all cases, but net torque is 0 in these two cases. So these two are equilibrium cases. However, there is a difference between this equilibrium state and this equilibrium state. Can you think about what that difference is? Well, let's come over here. Let's disturb this equilibrium. Let's say I twisted this or I tilted this dipole a little bit. What's going to happen? Well, remember this is being pulled this way, this is being pulled that way. A torque will come back, so there'll be a torque acting back on it, and it'll go back to its equilibrium position. If I tilt it this way, something very similar will happen. Torque will come back on it. Torque will make sure that this thing comes back to its equilibrium position. So if you disturb this equilibrium, it comes back. Nature likes this. We call such equilibrium stable equilibrium. because the name itself tells you it's very stable. You disturb it, it comes back. But what happens over here? Let's see. If I disturb this one, let's say a little bit, what direction will be the torque? Well, the positive charge gets pushed to the right, negative charge gets pushed to the left. Look, it's gonna turn all the way like this and come to this position, which means our equilibrium position would be lost. So you disturb it just a little bit. The equilibrium position will be lost. If you disturb it again this way, you'll find the same result. Equilibrium position will be lost. And therefore, this equilibrium is what we call unstable equilibrium. Again, because as the name suggests, you disturb it a little bit, you will not get this equilibrium back. So theta equal to 0 represents stable state. Everybody likes that, everybody's happy. Theta is equal to 180 degrees, also torque is 0, but nobody's happy. The electric field is not happy. It wants it to align the dipole in this direction. So disturb it a little bit, it gets the opportunity, puts all the torque, aligns it in the stable state. And therefore, this is an unstable equilibrium state.